Guys, welcome to the new video. Today we are going to discuss the topic of types of analysis in asymptotic notations in this algorithm code. So let's get started. Algorithm test we discussed earlier this. The time complexity of this is 4n square plus 18 plus 6, the order of n square, right? To determine the time of the algo under the a priori analysis, order of magnitude. A priori means this doesn't give you fixed, not give fixed value. It gave order of magnitude of a statement step of the algorithm refers to the frequency count of the fundamental operation in the uh, statement or step, right? It counts the frequency or count of the fundamental step operation, right? So magnitude of the what is it? Magnitude, order of magnitude, right? What refers to this. Then algorithm sum ABC. This is our I, what I say what I say this is our algorithm sum algorithm. These are integers ABC, read comma b if a is less than b. This is the this is a fundamental operation of read. This count for 1, right? This is comparison. This is a fundamental. This is assignment. This is fundamental one operation. This is multiplication and print. This is the operation. So here 1, 2, 3, 4, 5. This is order of 1 is the time complexity of this problem. All right, order of 1, which is because constant. What is whatever the constant, the time complexity is order of 1 always. Algorithm do it. Let's say this is the algorithm. All right, integer n and an, this is an array an, this is the value n, integer I, sum is equal to 0. These are two variables I and sum is equal to 0 is initialized. For I 1 to n, sum is equal to sum plus ai. So how many times it will repeat? N times. All right, this fundamental operation takes place n times, and this is for 1 times. So it is n plus 1 times. It will repeat itself. The fundamental operation, this will be order of 1 time, n time. All right, so this is the case how you do it. The order of magnitude. All right, so the basic objective of a priori analysis is to represent the time complexity. How will we do this? Let's say this is the time. I think this is the time complexity running time of the algorithm by means of a mathematical function with respect to input size, right? A mathematical function with respect to input size. This is the time complexity running time of algorithm by means of mathematical. All right, so 1 plus n square. This is the order of n. This is input size n, and n plus 1 and 4c. This is the rate of growth of time. All right, so time is directly proportional to function with respect to input size n, right? So it could be two types, polynomial or exponential. N to the power x is polynomial, x to the power greater than or equal to 0, right? N in square, these are subpolynomials. Linear, quadratic, cubic, right? Cubic, and this is exponential e to the power n, e to the power n. This is exponential functions and factorial also. So logarithmic also come under polynomial functions. So log n, log 1, and log n, these all are polynomial, all right? So what do you say that the exponential function have higher rates of growth, takes more time, all right? So let's say this is the quotient n square here, n is equal to 2, this is 4, but about 3, this is n, this is 8 to the power n, and to the power 2. But for after 4, it grows, exponential grows much faster than polynomial, right? Polynomial function have lesser rate of growth, takes less time, all right? Yes. So the objective is always to develop algorithm for problems having polynomial time complexity efficient uh, What is this? Objective is always to develop algorithm for problems having polynomial time complexity, which if the problem has polynomial time complexity, then it is efficient. It is called efficient, right? Algorithm. Yes, complexity theory. A priority analysis to determine the running time with respect to increased input size and to observe the behavior of the algorithm for a fixed input size of n. Behavior types of analysis. Algorithm, this is algorithm integer time complexity for 1 to n. If this is print I exit. Best case, if time complexity, best case that 1 plus 1 plus 1 is equal to c constant, worst case n. So yeah, if we are trying to if this is the first one unit time here, 2 unit times. All right. So I1, I2, I3 instruction, increment, decrement, random, IK time complexity, worst case. All right. Time complexity is measured in worst case only. All right. So worst case, if the input class for which algorithm takes max time, the input class for which algorithm takes max time in which input and corresponding time is worst case time. Time is worst case input and corresponding time is worst case time. Best case, the input class for which the algo takes minimum time is best case input and best case time. Alright. Average case is derived in three steps. Environment all enumerate all input classes I1 to Ik. Determine the time for T1, T2 and associate with each input class with probability of it Pi. Probability function Pi. So this is the probability function. I is sigma is equal to 1 to k are the classes, input classes, right? And Pi the probability of that, what of Ti, the time consuming, this is the average time, right? This is the linear search, best case big order of 1, worst case order of n, average case for the successful linear search. Number of comparison 1, 2, 3 and n plus 1 by 2 by n, right? So 1 plus n by 2 big order of n, right? Best case is less than average case is less than worst case homework. All right. Best case, average case, and worst case, merge sort, selection sort, heap sort. They are all worst case for linear search is order of n, but best case order of 1. So this quick sort log n for best case and log n, right? But n order of n square is for worst case. Analysis algorithm involves thinking about how their resources requirements, the amount of time and space they will scale with increased input size. What the fuck? Analysis algorithm involves thinking about how their resource requirements, and the amount of time, space they will use scale with increased input size. Right. Proposed definition of efficiency. An algorithm is efficient if the implemented it runs quickly on real-time inputs. So what is this saying is proposed definition. Alright, proposed definition of efficiency. An algorithm is efficient if when implemented it runs quickly on real input instances. Proposed definition of efficiency. Algorithm is efficient if it achieves quantitative better worst case performance in analytical level than brute force search. Alright. The proposed definition of efficiency algorithm is efficient because of polynomial running time. Alright. Brute force. Best case, worst case, average case. Average case is this, worst case is this. Problem size, number of steps, best case. Alright. The first case algorithm is the function defined by the maximum number of steps taken in an instance of size n. That means is the function defined by the maximum number of steps taken in any instance of size n. This represents the curve passing through the highest point in each column. This represents the curve passing through the highest point is the function defined by the maximum number of steps taken in any instance of size n. This represents the curve passing through the highest point in the column, each column. Best case is the function defined the minimum number of steps. Yeah, average case is average number of steps. Like so, we will do the next video, or we will should we continue in this one only? We should continue in this one only. So how we will do this? Delete, and we will insert our new file attachment from here. I think 4 number. Yeah. So we will see what is this all about. Lesson number 4, class notes, processing the document. My PC is getting slower and slower every day. I think it's, yeah. Welcome. Let's continue lecture from here. This is our dear sir, I mean the Khalil sir, Khan, Dr. the Khalil Khan sir. He is a very good teacher, very good teacher and a gentleman also. But if analysis we saw in previous types of analysis, we saw worst case and best case, we will cover in this. Ah, count. Asymptotic notation, big O notation, omega, big omega, theta notation, small notations. We will see in this lecture a little bit. Alright. So what's in this? Let's see. Time complexity, let's say polynomial, log, constants, quadratics, cubic. These are all polynomials. Exponentially a to power n exponential. We all know that. Alright. So to represent these asymptotic notations, we use asymptotic notations. Alright. So asymptotic notations, math tool to obtain or represent bounds of functions. Alright. So upper bound max, lower bound minimum, tight bound. Alright, we will see in tight bound. So represent time and space complexity of algorithm by functions, which is asymptotic notations. Right, upper bound max, lower bound minimum. So how can I explain to you this, that if this is a floor, this is a person right here. So what is the upper bound for this? Is 10. What is the lower bound for this? Is this whole, like, I don't know how to do it. So let's quickly skip that. Upper bound is big O notations. Alright, it can to go from here. Alright, and yeah, small little o, big omega, lower bound, upper bound, lower bound, and tight bound is theta. Small little o notation, little omega notation, proper upper bound, proper lower bound. This is called, right? Alright. So let f and g be functions from the set of integers or real numbers to real numbers. Right, big O notation upper bound. Fn is a big O of Gn if there exists some constant C for which, right, such that Fn is always less than to C of Gn, right, whenever n is greater than or is equal to n0. There is a input size n0 for which, right, big O of Gn, Fn big O of Gn set. So let's see how is this. Fn 1 if we exceed the size of n, then 1 plus n is negligible in let's say 1000 to square, which will be 10 to the power 6 right? 1 2 3 4 5 6, and now 1000 is negligible. Uh, what we say in comparison to this, all right, 10 to power 6, all right. So 10, I think 1 million is this, yeah, 1 million, right? So this will be, we will say that it is a big order of n square, all right. So how will say that? Big order of n square, 1 plus n square, n square, n square, n square, fn 3n square will n square greater than 1 and 0. So there is some constant always, right? Fn is cube, n is 1 plus 2 is 5, fn is a big of n square, f is big of n cube, yes. If it is a big of n square, then it will be n cube also, n 4 also, but the closest and the tightest upper bound is this, and this is the more uh, correct. Whenever we determine the upper bound lower bound, we should find the function g which is closest to the given function, all right. So which is the closest, we will count this, all right. So construction 5, what is this? LB. So this is the some example given by the, all right. Businessman Ambani investments worked cycle 15 crore, 0 would be of crores. So we will big of crores, yeah. Big omega notations are lower bound. Fx is big omega of Gn if and only if there exists a constant C and n naught such that Fn is greater than always, alright? If n is greater than always for C or Gn, whenever n is greater than n0, right? Fn is 1 plus n square or n. So it is a big omega of 1, it will be big omega of n or omega of n square also. So greater than is equal to, yeah, omega of n square. What we will say is here omega of n square, we will say it is the closest one, right? So n square, this is C here, this is G here, this is how we say it, right? Make theta notation. If f is theta, if and only if is fx is g of n and f is omega of n square, then theta of n square, all right. Then c1 dot gn less than equal to fn and less than equal to c2 dot gn. What is this case? Yeah. So let's read the some content from here. Big O notation is a mathematical notion that describes the limited behavior of a function. Alright. When the argument tends towards a particular value of infinity, Big O notation is a member of a family of notations invented by Paul Benjamin and Edmund Landua and others, collectively called Benjamin L notation or asymptotic notations. The latter O was chosen by Benjamin to stand of ordinum, alright, meaning the order of approximation. The computer big O notation is used to classify algorithms their runtime and space requirement to provide input size it grows, alright. So in analytic number theory, big O notation is used to express a bound on the difference between an arithmetic function and a better understood approximation. A famous example of such difference is the remainder term in the prime number theorem, right? A famous example of the difference. All right, we will do that. Big O notation is also used in many other fields. Let's see how to provide similar estimates. In which fields? Big O notation characterizes functions according to their growth rates. Different functions with the sorry, wrong, right? Different functions with the same asymptotic growth rate may be represented using the same O notation. What let's say different function with the same asymptotic rate may be growth rate may be represented using the same big O notation. The latter O is used because the growth of rate of a function is also referred to as the order of the function. A description of a function in terms of big O notation usually only provides the upper bound on the root of the function. Associated with big O notations are several related notations using the big O for n omega and theta and small omega to describe the kinds of mounts associated to rates. So definition: a theoretical measure of the execution of an algorithm. A theoretical measure of the execution of an algorithm. Usually the time or memory needed given the problem size n, which is usually the number of items. Informally saying some equations n fn of gn means that it is less than some constant multiple to gn. The notation is read if f of n is big of f of n is big of g of n. Well, this is how we see that f of n equal big of g of n means that there is a positive constant c and k such that f n is greater than 0 is less than c and k, or k value c and k the most fixed values function must be fixed for the function f n must not depend on n. Alright. Big omega notation similar to big O notation. Big omega function is used in computer science to describe the performance or complexity of an algorithm. So computer science should describe the performance and complexity of algorithm. If a running time is if a running time is this omega of n, right, big omega of n, then the large enough n, then the for large enough n, the running time is at least k dot fn, right, for some constant k. The formal definition is associated with big notations as follows: big is c dot is upper bound of fn, thus that there is some constant c such that we always less than this or large enough n is used for something also. There is a lower bound of fn, thus there exists some constant c such that fn is always greater than c for some constant gn, right? For all n is greater than or equal to n0. So this is the big O of nitrogen. This is the n naught here, and it can vary here. But for this, it will O of gn fn. There exists positive constant c and n naught such that O of gn cn for small n exists in n naught. We write fn is equal to big O of gn to indicate that the function of fn is a member of set big O of gn. Note that fn theta gn implies fn is equal to, since theta notation is a stronger notation than notation written said theoretically big omega notation. This is the big omega. Fn is always higher than this, right? Value. Fn, which means this is the upper bound of Fn. F theta of Gn means the C1 Gn is upper bound of Fn, and C2 Gn is a lower bound of Fn, and for thus that there exist constant C1 and C2 such that Fn is less than equal to C2 Gn. This means that a nice amount on Fn. Say Fn, yeah. So it's how we do. N naught is the fixed and function. We go Fn square and we got Fn square also. How will we do that? Because Fn will always greater than or equal to n square. Right? Yeah. And we go from theta of n, we will do this. We have 100, we go 1, we have 1, theta of 1. Yeah, this is how we do. Thank you so much. We will meet you in the next video. So n plus log n, we go to n, and we will take the major part of the approximation with this. Yeah, thank you so much. We will meet you in the next video.